So this is my lab this week on the motion of falling objects. My name is Zukar Islam and I'm in lab section MO8. So the objects that I observed for this lab are a water bottle and a coffee filter. And for the gravity portion of this lab, I came to the chief result that an object with only the force of gravity acting on it will have a constant acceleration, and thus the speed of the object will increase until it is done falling. And that's because the F net does not equal 0. And then for the drag force portion of this lab, the same objects were under observation, and I came to the chief result that an object with both gravitational and drag forces acting on it will accelerate or decelerate until a terminal velocity is reached, and from then on it will continue to fall with that same constant velocity. And the F net does not equal 0 for that part either until it reaches that terminal velocity. And so this is the video that I actually used for the lab. Here's the water bottle, and then here's the coffee filter. I set the origin at the bottom of the water bottle because I wanted both the filter and the water bottle to start from the origin, and they're starting from rest. And then it's going to fall along the negative y-axis, which is this purple line right here. And so the length scale for this is about 4 inches, which I converted to be about 0.1 meters. Which is the length of the water bottle that is initially shown in the video, and that doesn't change throughout the video. And for the time scale for this is about 0.4 seconds for the water bottle and 1.1 seconds for the coffee filter, and that's how long it took to actually fall. And so here it is falling. The blue diamonds are the water bottle's average position as it falls, and the red diamonds are the coffee filter's position as it falls. And so after I used the tracker to get some data, I used that data to write some programs to model the fall of both the water bottle and the coffee filter. So here are the system properties and initial conditions for the water bottle and the coffee filter. As you can see, they're really similar except for the masses of both the objects. They're different, but the position and the velocity vectors for both are 0. And the time step is about 1/30th of a second, because that is what tracker told, like that's the way tracker set it up, is each time interval was about 0.03 seconds. And so the code that only involves gravity is being shown right here. The yellow boxes indicate where gravity is actually used in the code. So the gravitational force is -1 times the mass of the object times gravity, and that's the y component of the vector, and it's used to calculate the velocity as it falls. And I'm just going to run that program for you guys really quick so you guys know what it looks like. So it's taking a second to start up. So there you go, there's the plot, the data points for that. And then so for the data I got from the models and from the tracker video, I was able to graph them on the same line, on the same graph. So the green indicates with only just the force of gravity acting on it, and as you can see, that is the curve, but the data from the observation isn't exactly that curvy. It comes to some kind of constant slope, and the same thing happens with the coffee filter. The data comes to some constant slope, but the model with only gravity acting on it is a curve, and the slope of the line is representative of the velocity. And so the part of the program I wrote that involves drag force is being shown right here. The yellow boxes indicate where drag force is actually being used. The drag force vector is right here. It's b, which is some constant of proportionality, times the magnitude of the ball's velocity, because drag force does oppose velocity. And so that will give you an F of net force of gravity and drag force, and that net force is used to calculate the velocity right here. And so again, from this model I was able to get more data, and I plotted that on the same graph as I got from the tracker video. And for the water bottle, as you can see, both the lines start off curvy and then they come to like some kind of slope, and that slope is representative of the terminal velocity. And the same thing happens with the coffee filter. Both the lines come to some slope, and that slope is the terminal velocity. And so what does all this mean? Well, it means that both objects not only experience a gravitational force acting on it, which causes it to fall, but they also experience another force called drag force. That drag force is a force that opposes the object's motion, and with the presence of a drag force, the object should come to some terminal velocity, and thus the model including drag force predicts the terminal velocity. And so then this leads to the what if. So what if the slow falling object was thrown with some initial velocity? Well, I wrote a program for that, and the only thing that changes in the program is that the initial velocity right here would just have a different value. It wouldn't be 0. So I would just put -5. And so when only gravity is present, all this means is the object will travel with a faster speed throughout the time interval. It will hit the ground with a faster speed than it did without an initial velocity. And then so what if the same condition occurred, but when drag force and gravity are both present? This just means that the object will travel with a faster speed throughout the first part of the time interval, but the terminal velocity will still be the same regardless of the initial velocity. It will just reach that terminal velocity quicker. This is because the terminal velocity is dependent on mass and surface area. And also, in order to get that terminal velocity, the net force has to equal 0 at some point. And for that to happen, the gravitational force and the drag force have to be equal to each other, but in opposite directions, or opposite values. And so since the gravitational force does not change at all, the drag force will not really change either, and thus the terminal velocity will not change. And I'm just going to show you a quick program that I wrote for that, just so you guys have a visual of what it looks like. So as you can see, it starts off a little bit different, but ultimately the slope becomes constant, and that slope is the same terminal velocity. Well, thank you for watching the video, and I hope you guys enjoyed it.